Welcome, honor students. Today we will begin chapter 15. So the last 3-4 weeks of school, we are going to be in what's called aqueous solutions. And reactions that deal with aqueous solutions are a big part of chemistry. So we will go through chapter 15. We're not going to go and spend a lot of time in 15. A lot of 15 is actually a review. You will see that as we go through the lesson today and in next week. So we're going to be in chapter 15 all of next week, and then we're going to jump into 16. So when we have our test, it'll be on the concepts of 15 and some of chapter 16, and I will specify to you at a little bit later date which ones that will be. But for today, these are on Moodle for you already. We're going to begin chapter 15 and the study of water. So you're already somewhat familiar with it, and hopefully a lot of this lesson will be a review for you. So what properties of water make it essential to life on Earth? So water covers, it says 3/4, it's roughly about 71% of the Earth's surface, water covers. And it is crucial to life. Why? When you stop to think about it, an adult human is around about 68 to 69% water. So that's why it's so important. We are composed of a lot of water. Now, if you talk about specific organs, they're even more water percent. But in general, even bones, you think of water to bones, but they're about 13% water in them. So a lot of water, and that's why it is important to life. But there's other characteristics of water that are important as well. So what factors cause the high surface tension, low vapor pressure, and high boiling point? So we study these terms and these concepts. Hopefully some of these things will come back to you as we talk about it. So when we talk about the Lewis structure, so you guys remember Lewis structure. So we have Lewis structure of water. Remember, we're only dealing with valence electrons with the outer shell. And when we draw this out, we have something that looks like this. And we have to have these two unshared pairs represented, or the Lewis structure is not correct. So oxygen came in with 6 valence electrons, and hydrogen provided 1 each. So if you remember the regular Lewis dot structure, and oxygen was 1, 2, 3, 4, and let me back up here. And that was the Lewis structure that we were familiar with. And when hydrogen comes in with its 1 each, it comes in, and then we talked about the Vesper theory, the valence electron shell repulsion theory, and why it gets this shape. So when you draw this out here, we have a bent molecule. And when we look at this as a bent molecule, we have a bond angle of 104.5 degrees. And the reason for that is because of these 2 unshared electron pairs right here and here. And they pull closer to the oxygen, and therefore the hydrogens have to move and kind of push back a little bit, and that is why it has a 104.5 degree bond angle. So when we look at this shape here, we have our oxygen. I'm going to redraw it like this right here, so I can talk about it a little bit more clear. When we talk about what type of bond we have here, we have a covalent bond, and particularly it is a polar. Remember electronegativity. So oxygen is very electronegative. Because it is electronegative, it is holding the electrons very close to itself. So when you talk about it holding the electrons close to itself, it will get what we like to call a slight negative, which is going to be a delta negative. And this side here is going to become slightly positive, and we can say delta positive. So this is a polar molecule. It's polar. So when we talk about polar, it has definite areas, and it has a dipole moment. When you talk about a dipole moment, it is a molecule that is asymmetric, and it has areas of polarity. And we draw it, if you remember, hopefully you remember, that is how we would represent a dipole, where the plus right here is designated, this is slightly positive, and this end over here is slightly negative. This is very important. So when you talk about this being a polar molecule, now you have intermolecular forces, so that is between molecules. So you have these molecules, and you have water here. Let me just draw another water right here. And then you have a attraction that takes place like so. We have these two unshared here. There is attraction between this unshared electron pair on that water and this slightly positive hydrogen. And remember, because this is slightly negative. So because this is a hydrogen and an oxygen, this is a special type of attraction, intermolecular force. It's called hydrogen bonding. So this is H bonding. So hydrogen bonding, if you remember, occurs only between hydrogens and fluorine, oxygen, and nitrogen. That's it. Those are the only three. So water has this. So just imagine this is going on all throughout. This is the reason for all of these specific properties that you see listed here. High surface tension, low vapor pressure, high boiling point, because that hydrogen bond is going to take a lot of energy to separate. So therefore, this is really important. It has, it's a polar bond, it's a polar molecule, causing it to have dipole interactions, and this particular dipole interaction is called hydrogen bonding. All right, so moving on a little bit. I know I spent a little bit of time there. Hopefully you took some notes on that. Those are real key concepts that you're going to have to know for this particular chapter. So water, the H2 molecule, is a simple molecule, just 3 atoms. We talked about that. Oxygen is very electronegative. We talked about it. It's up at the upper right quadrant of your periodic table, and therefore it really attracts electrons to itself. Hydrogen, not so much. So it is highly polar, and you remember the Pauling scale, and we could calculate these numbers out. So here's what I drew, and this is a nice shaped geometrical shape here, so we can actually see this a little clearer. And here's our dipole moments drawn out for us. So it gets these slight negative up here, slightly negative, and each one of these are slightly positive. And you see that listed right here for us. So real important that we have that. And the less electronegative hydrogen gets that slightly positive charge. So how do the polarities of the 2 OH bonds affect the polarity of the molecule? Well, it makes, because it's asymmetrical, notice that they don't cancel out. It can't cancel out because of the shape, so that you have this distinct area. So where the hydrogens are, it is positive, and then up here it's negative, so therefore it is a polar molecule. So the bent shape is what actually causes that. The 2 OH bond polarities do not cancel, so the vectors, if we calculated vector forces, they do not cancel out, so therefore it remains as a polar molecule. So many unique and important properties of water, including what we talked about earlier, are attributed to this, the hydrogen bonding. Why is it? Because it's the strongest of the intermolecular forces is the hydrogen bonding. So surface tension, let's talk about each one of these properties. So surface tension. You've noticed that water forms these spherical drops. So if you spilled water on a table and you look at it, it's not normally, unless it's like a really big amount of water, it's normally not just one big puddle. You see these little distinct puddles. And why is that? That's really because of the surface tension and it pulling in on itself. So let's talk about that. So let's look at this picture here. Here we have this drop of water, and you see all these hydrogen bondings taking place. All these molecules are all interacting with each other and attracting. So the water molecule within the body of the liquid form these hydrogen bonds. The attractive forces of these molecules are balanced, and the water molecule at the surface is unbalanced. So that's why you see it start to pull in. As a result, the water is drawn inward, and that's what makes these puddles, these little puddles or droplets that you end up typically seeing when you see water spill. So that's a definition, so please get this into your notes. The inward force or pull that tends to minimize the surface area of a liquid is called surface tension. All liquids have surface tension. It's not just unique to water. But water's is higher than most because of H bonds. The hydrogen bonds make it much stronger. So the surface tension of water tends to hold a drop of liquid in that spherical shape or trying to pull it. It works out really good if you see if a waxy surface or a table that has a nice polish, you drop water, you'll see it beat up in those little droplets, and that's because of surface tension. So you can decrease the surface tension by adding what's called a surfactant. So please get that into your notes right here, a surfactant. Surfactants is any substance that interferes with hydrogen bonding between water molecules and reduces its surface tension. And that is exactly what soaps and detergents are. They're called surfactants. So they have the ability to break up a polar and nonpolar and get a nonpolar to dissolve. So what it does is, if you have grease, part of the soap or detergent bonds with the grease, and now, because remember, oil and water don't mix because it's polar and nonpolar, and polar dissolves polar, but it will not dissolve nonpolar. And because of this interference, and it actually allows now the water to break up the oil droplets. So surfactants are really important. It's, once again, the definition: any substance that interferes with the hydrogen bonding between water molecules and thereby reduces the surface tension. And it also allows it to break up oils and greases, whereas water typically wouldn't do that. It's a real important concept. So vapor pressure, let's talk about vapor pressure. So remember what vapor pressure is. It is the force above a liquid. So if you had a puddle of whatever liquid you have, those molecules on the surface can overcome the attraction to escape into the atmosphere, and that's the vapor pressure. And we studied that in chapter 13, and this still applies. Why is water's vapor pressure so low? It's not high. If you spilled water and you spilled some alcohol, alcohol would vaporize and be gone relatively fast. When you talk about water, you spill it and it's going to be still sitting there for a while. That's really important. It evaporates slowly. Why? Because the surface tension is there, and in order for it to escape into the vapor, into the gaseous form, it has to overcome the hydrogen bonding. So an extensive network of hydrogen bond holds a molecule of liquid to one another, and these must be broken before it can go into the vapor state. So that's why it is a slow process to escape. So once again, we talked about alcohol pretty much very typically will evaporate very fast. And that's because it has a high vapor pressure, whereas water tends to linger for a while. Now, boiling point, same process. The molecular compounds of molecules are typically low. The melting points are very low typically. And in many cases, at normal temperatures, they're gases. But water, because of hydrogen bonding, is a liquid at room temperature. And look at the difference. So here we have ammonia, which is a gas. And look at where it boils. So it is a gas at room temperature. So it boils at negative 33 degrees Celsius. And it is NH3. It's 17 grams per mole. If you talk about H2O, you are talking about 16, 17, 18.02 grams per mole. Very close, but yet look at this. Huge difference in its boiling point. Why? Because of all these intermolecular attraction, the hydrogen bondings. Yes, all covalent compounds have London dispersion forces, and that's the momentary attraction caused by the movement of electrons. We talked about London dispersion, so they're always there. But hydrogen bonds are special polar molecule bonds that have this strong attraction, and it only is between the fluorine, the oxygen, and nitrogen and hydrogen. And this is a special bond. Hydrogen bonds are very strong, and thus this is why you have such a huge difference. Negative 33 in a gaseous state, and water is a liquid at room temperature and a boiling point of 100 degrees Celsius. And it's attributed to the intermolecular attractions of hydrogen bonding. So the difference between that is all due to hydrogen bonding, which is very extensive. So, checkpoint question. Some insects are able to walk across water. How do the properties of water explain their ability? Hopefully you can think about this and process why that is. It's the surface tension. It's because the water, the same reason if you jumped in a pool on a belly flop, why does it hurt? Well, because the water doesn't want to be pulled apart. It is attracted, and those hydrogen bondings are holding it together, and therefore that is why the surface tension allows it to do that, surface tension, and that's why it does not sink. So let's talk a little bit about the solid state of water. And when we talk about describe the structure of ice, it's a solid. I mean, that is pretty straightforward as far as that goes. But let's think about its density. When you talk about typically water, when we talk about its density is labeled as 1. When we talk about ice, it floats, so its density therefore must be less than 1. So its solid state is less than its liquid state, and that's unique to water. So ice float in your glass of iced tea because solid water has a lower density. So please jot that down, lower density. This situation is not usual. It's very unusual that the solid is less dense than the liquid. Normally the solid is more dense. That's why it's a solid, but water has this special quality. And this is really important to life that this process occurred. Now, ice floats, we know that, but you can make ice not float. And that is if we used deuterium, which is a heavy hydrogen. It's a hydrogen that has an extra neutron in its nucleus. And if you had that, you could actually make ice and it would not float, it would sink because its density would be higher. But we're not talking about exceptions. That's a kind of a neat demo. If we were in the class, I was going to talk to us about that particular activity. But nevertheless, we're talking about just regular regular ice with regular water, and it is less dense than the liquid form. All right, so let's look here. As water begins to cool, it behaves like any typical liquid. So if you're at 100 degrees, look at what's happening to right here. Goes from 0.95, 0.98, 0.99, 0.997, then you get to about 4 degrees Celsius. It's at 1 grams per centimeters cubed. But then as you hit 0 degrees Celsius, remember that is in equilibrium with solid and liquid. Look at what happens. You fall, and when you actually hit into the full solid state, you are 0.9168. So you are less dense than the liquid, and that's why the ice floats. So that is really important. So why is ice less dense? Let's think about that. It has to do with the hydrogen bonding. So the hexagonal symmetry of a snowflake reflects this crystal structure. So think about what's happening. It's going to arrange itself. So because of all this attraction, right before it freezes, it slightly expands. So remember, positive and positive and negative. So if right before, let me just draw 2 water molecules here. And this side here is negative and this side here is negative. Right before it turns into its solid state where it will be rigid, any positive on positive, negative on negative will slightly repel out. And that's why it slightly bulges and becomes less dense. So that's a unique property, and that's really important, and that's why it becomes less dense. So the unique property of ice results from this hydrogen bonding. So another reason for it is this extensive hydrogen bonding holds the molecules further apart. Plus, it gets this ring structure that takes place. In that, it also allows it to be less dense. Remember the attractions. It does not want to have positive on positive, negative on negative. So it will slightly repulse, and therefore you have these ring structures that form right before it turns completely solid and rigid. So now they're going to be further apart, and it's going to be in an orderly arrangement, and now it's less dense. So the fact that ice floats is very important to life in general. Think about that. The reason that fish and many other organisms survive is the fact that the surface is what freezes. Even if it's 1 foot thick, you still have water. Think about ice fishing, Alaska, upper northern Canada. There was places like that. People actually ice fish. They drill holes, drop down line, and they fish. How is that possible? Only because ice floats. If it did not, all that life would be dead. It would die. It would kill it. So if ice were denser than liquid, the bodies would tend to freeze solid during the winter and destroy all organisms that live in it. So real important to life. So what properties of water that are essential for hydrogen bonding make it essential to life on Earth? Think about that for a second. Well, lots of different reasons here. The low vapor pressure keeps the water on Earth and don't allow it to evaporate quickly. So real important, that low vapor pressure is what allows ponds to stay there and rivers to not just evaporate up. If water did not have such a high boiling point, it would be a vapor at the usual temperatures we have here. So if it was like any other liquid, it'd be in a gaseous form because basically its size and how small it is would be a gas, but the hydrogen bonding is very important. The fact that ice floats also allows, so these are the 3 points. Please make sure you notate them, of why it is essential that water has the properties that it has. So checkpoint, last question here. In ice, how many hydrogen bonds can be formed between one hydrogen atom of a water molecule and the oxygen in the surrounding water molecules? Think about this. Let's ask. Here you have a hydrogen hydrogen bonded to our oxygen. I have to have my 2 unshared pairs. And I have another water molecule right here. And these are my unpaired shares. So it's asking between this hydrogen right here, how many hydrogen bonds can it form? Well, it's going to be attracted right here to this unshared pair right there. That unshared pair it's going to be attracted to. So you could say it could only have one. And this right here should be what your choice is. And that is the correct answer. So that is it on 15.1. We talked about the unique properties of water. We drew Lewis structures. We talked about hydrogen bonding. Talked about shape. We talked about bond angle, 104.5. The structure of ice, it's less dense than its liquid state. We defined and talked about surface tension. We talked about a surfactant and bonding and interactions and its essential qualities to life. That is it on today's lesson of 15.3. So I will have another lesson posted for you on Friday of 15.2. So thank you for watching. Go in peace.